the lecture. Yesterday, we were discussing about 3-bit asynchronous up-down counter, or this is also called as bidirectional counter. It can count in both directions, up as well as down. Okay. So here we are using 3 JK flip-flops as usual in toggle mode. Okay, and along with these flip-flops we are using some extra logic using and OR gates. Okay, so now with help of this extra logic, this particular circuit is working as a bidirectional counter. That is, it can count in up as well as in down direction. Okay, now let us see what happens when up is equal to 1 and down is equal to 0. Okay, so let us see what happens to the different gates which are present here. So as you can see, this is a set of 2 AND gates and 1 OR gate. Okay, so inputs of this upper AND gate, let us call this as 1, 2, and this gate as 3, and this is 4, 5, and this gate as 6. Okay, now if one of the inputs of AND gate number 1 is 1 and another input is Q0, and therefore output of AND gate number 1 is Q0. Okay, so now if you see this second AND gate, one of the inputs is Q0 bar and other input is 0 because our down line is equal to 0. So 0 multiplied by anything will be 0, and therefore output of second AND gate will be 0. So now inputs of third OR gate, they are Q0 and 0. So what will be the output of OR gate? It will be Q0 plus 0, which is equal to Q0. This means this is as if you are applying Q0 to the clock. You are applying Q0 directly to the clock. Now similarly, let us see what happens in this second logic circuit. For AND gate number 4, you can see one of its input is at logic 1 and another input is Q1. So output of AND gate number 4 is equal to 1 into Q1. So 1 into Q1 is equal to Q1. So at the output of AND gate 4, we have Q1. Okay. Now if you see fifth AND gate, one of its input is Q1 bar and another input is 0. Okay, this input is 0 because our down line is 0. So 0 into Q1 bar is equal to 0. So output of the fifth AND gate will be 0. Now you can see inputs of OR gate number 6. They are Q1 and 0. So output of OR gate 6 will be Q1 plus 0. So it will be Q1 plus 0, which is equal to Q1. That means it is as if you are connecting Q1 to clock of flip-flop number 3. So these connections are connections of up counter, and therefore when up is equal to 1 and down is equal to 0, the counter is working as up counter. Okay, so in this way the counter is working as up counter. Now let us see when the counter will work as down counter. Okay, so for down counting, here I am going to write for down counting. Your up line must be equal to 0 and down line must be equal to 1. So if you are doing your control signals up and down, these are called as control signals, and if up control signal is 0 and down control signal is 1, your counter will work as down counter. Let us see how it works. Okay, so in this case, now up is 0, up is 0 and down is 1. Okay, so now if up is 0, one of the inputs of AND gate number 1 will be 0 and therefore its output will be 0. Now down is equal to 1, therefore one of the input of AND gate number 2 is 1 and another input is Q0 bar. So output of AND gate number 2 will be Q0 bar into 1. So Q0 bar into 1 is equal to Q0 bar. Okay, so the now the inputs to gate number 3, which is OR gate, are 0 and Q0 bar. So output of OR gate will be 0 plus Q0 bar, which is equal to Q0 bar. Okay, meaning of this is that the Q0 bar is connected as a clock of flip-flop number 2. Okay, now similarly, you can consider the second logic circuit, and for this, here you can observe for gate number 4, which is AND gate, one of its input is 0, and therefore its output will be 0. And for AND gate number 5, one of its input is 1, and another input is Q1 bar, and therefore its output will be 1 into Q1 bar, which is equal to Q1 bar. So here output will be Q1 bar. Now inputs of gate number 6, which is OR gate, they are 0 and Q1 bar. So output of OR gate number 6 will be Q1 bar plus 0, which is equal to Q1 bar. So this is as if you are connecting Q1 bar to the clock of flip-flop number 3. So these are connections of down counter. And therefore, in this condition, that is when up is equal to 0 and down is equal to 1, the circuit is working as down counter. Okay. So are you clear about this? Yes, write in the chat box. Are you clear about this? You understood? So that we can move ahead. Because this much one only you have to remember for up down 3-bit asynchronous counter. Okay, so are you clear? Type in the chat box so that I will come to know that we can move ahead. Or else if you want something explained, ask me. You can ask me. Yes, Sakshi, you have any doubt? Sai, Atharva,
No, ma'am.
okay. So I think we will move to next type of counter. So here we have finished asynchronous 3-bit counters. So like this, you can extend this to 4-bit counters. The same working principle will be there. Only in case of 4-bit counters, there will be 4 JK flip-flops. Okay. And in case of 4-bit counters, as there are 4 JK flip-flops, 2 raised to 4, which is equal to 16 states it can count. So 4-bit counter can count 16 states. So you remember this. And suppose if you want to write the working of 2-bit counter, then in that case, what you have to remember is you have to use only 2 JK flip-flops. And 2-bit counter means number of state is equal to 2 raised to 2, which is equal to 4. So 2-bit counter can count 4 states, 3-bit counter can count 8 states, and 4-bit counter can count 16 states. Okay, so 2-bit counter will require 2 JK flip-flops, 3-bit counter will require 3 JK flip-flops, and 4-bit counter will require 4 JK flip-flops. Okay, so are you clear about this? Because what I have discussed now, it may be asked in examination for MCQ type of questions. This is very important. Are you clear about this? The relation between number of bits and number of states that counter can count, and number of JK flip-flops that you have to use, and the number of bits. Are you clear about this? Type in the chat box. Yes, somebody type. Okay. So this was very important for examination point of view. You can note down in your notebook. Okay, so the relation between number of states and number of bits. Okay, so I will write relation here so that either you can take a screenshot or uh, you can write it in your notebook. So that will be better, I think. So 2-bit counter, it will require 2 JK flip-flops in toggle mode actually, and 2 raised to 2 equal to 4 states it can count. Okay, 3-bit counter, it has to use 3 JK flip-flops and it can count 2 raised to power 3 equal to 8 states. And 4-bit counter, it has to use 4 JK flip-flops, 2 raised to 4 equal to 16 states it can count. So take a screenshot of this or write in your notebook because this is very important. Okay. Okay. Now what we will do is now we will move ahead with 3-bit synchronous counters. Okay. So today we will be studying synchronous counters, and synchronous counters are counters in which clock signal is simultaneously applied to all the flip-flops. Okay, and these type of counters, they are faster in speed and they require some external logic for its operation. So these two important differences between the synchronous counter and asynchronous counter you have to remember. Okay, so this is also again very important as far as your examination is concerned. So now let me write or let me draw the circuit diagram of the 3-bit synchronous up counter. 3-bit synchronous up counter. Three flip-flops we are going to use here, as there are three what you can say bits here. So either you can use JK flip-flop or directly you can use toggle flip-flop. Okay, so anything will do. So earlier diagrams I have drawn with JK flip-flop in toggle mode. Now I will draw the diagram using toggle flip-flop only. Okay, so let us call this as T0, T1, T2. Okay, Q0 bar, Q0, Q0 bar, Q1, Q1 bar, Q2, Q2 bar. Okay, so these are the inputs, and how the connections are done. So that is what you have to see. The first flip-flop is, its input is tied to logic number 1. One important thing you have to remember is that clock signals of all flip-flops, they are connected together and they are given to single clock source. Okay, so they are triggered simultaneously. All flip-flops are triggered simultaneously. That is what you can say. Now here you can see the Q0 is directly applied to T1, and here we are going to use one AND gate, and Q1 is applied as input to this AND gate, and Q0 is also applied as input to this AND gate. Okay, and output of AND gate is applied to T2. So this is what is synchronous connection with some extra logic. Okay, so this is your Q2 output. This is Q1 output, and this you can say is your Q0. So can you see the diagram properly? Can you see the diagram properly? Take a screenshot of this diagram or draw the diagram. Okay. So yes. Are you clear about this diagram? And where is Sai? Sai is out of network? Yes? Tell him to try once again. I will let him in. Atharva. Okay, let us see working of this 3-bit synchronous up counter. So in case of 3-bit synchronous up counter, the difference in the connections is that which I have earlier discussed with you. All clock signals of all 3 flip-flops are connected together. They are applied to a single clock source. Okay. This is your first flip-flop, and input of the first flip-flop is connected to logic 1. Logic 1. Okay. And output of first flip-flop is given as input to second flip-flop, and output of first flip-flop and second flip-flop, they are given as input to AND gate, and output of this AND gate is applied as input to the third flip-flop. Okay, so that means what? Whenever both the inputs, both the outputs of flip-flop number 1 and flip-flop number 2 are 1, then and then only the T2 will be equal to 1. Okay, otherwise it will not be. And when T2 is equal to 1, then and then only your flip-flop is going to toggle. That is, it is going to change the state. Okay. So now let us see working of this at quickly. So we have to see working quickly so that we can move to down counter. Okay. So here initially you have to assume the previous state of the counter, and let us assume the previous state as 0 0 0. So let Q0 be 0, Q1 be 0, and Q2 be 0. Okay, so if this is your previous state, now apply a clock pulse here. Okay, so when you apply a clock pulse, then what will happen? As logic 1 is applied, logic 1 is applied to T0, it is going to change the state from 0 to 1. Okay, now as you can see, earlier the output Q0 was 0. So this was 0 and this is also 0. So 0 into 0 is 0. So input which is present at T2 will be equal to 0. Okay. So input at T1 is 0. So it will not change the state. So output will remain as it is. It will remain 0. Only Q0 is changing the state. And input of third flip-flop is also 0, and therefore Q2 is not changing the state. So this Q2 is your MSB and Q0 is your LSB. So you have to read in this direction. So after 0 0 0, we are getting the next count as 0 0 1. Are you clear about this? Are you clear about this?
Yes, ma'am.
Yes, write in the chat box. Always write in the chat box. Yes, Sakshi, are you clear? Okay.
Yes, ma'am.
Sai, Atharva, what about you? Okay. So now let us go to next state. So discussing before discussing the next state, you have to confirm the previous state. Okay. So previous state now the previous state was 1 here, 0 here, and 1 here. Okay. Now, as inputs to AND gate are 1 and 0, its output will be 0. Okay. And output of AND gate is applied as input to third flip flop. So, input to third flip flop is 0. Okay. And here what you can see, input which is applied to second flip flop is 1. So now what are the input conditions? Here input conditions are very important. Input condition of first flip-flop is at logic 1. Input of second flip-flop is again at logic 1. But input of third flip-flop is at logic 0. Okay. Now when you apply clock pulse, you are applying clock pulse simultaneously to all flip-flops. So all flip-flops will be changing their states simultaneously. Now, as input of flip-flop number 1 is logic 1, it is going to toggle, and therefore it will change the state, and it will change the state from 1 to 0. As input of second flip-flop is also 1, it is going to toggle its state. Earlier state was 0, so now it will become 1. Okay, and as input of the third flip-flop is 0, it will not change the state, it will not toggle, and therefore output of this will remain as it is, so which was 0 earlier. Okay, so it will remain 0. So what are the outputs now in this case? Q0, Q2 is 0, Q1 is 1, and Q0 is 0. So this is your second count, 0, 1, 0. 0, 1, 0 in binary means 2 in decimal. So this is your second count. So when previous inputs are 0, 0, 1, and if you apply a clock pulse, then you will get output which is equal to 0, 1, 0. Are you clear about this? Are you clear about this?
Yes, ma'am.
Okay, now let us see about the next state. Because now, suppose if your previous state, in this case, previous state in this case is 0, 1, 0. Okay, so let us consider these outputs. Q0 as 0, Q1 as 1, and Q2 as 0. Okay. Now input to T0 is always logic 1. Now here you can see input to T1 will be 0 now. It is not 1. Okay, it is 0 now. And input to AND gate is 0 and 1, and therefore its output will be 0. So input to third flip-flop will be 0. Okay. Now in such condition of inputs, let us see what happens when we apply a clock pulse. So when we apply a clock pulse in such conditions, then as flip-flop number 1 is having input equal to logic 1, it is going to toggle. So it will change the state from 0 to 1. Similarly, you can observe flip-flop number 2 is having input 0. So as its input is 0, it will not change the state. So it will remain the same as it is, which was 1 earlier, it will remain 1. Okay, and even the input of the third flip-flop is 0, therefore it is not going to change the state, and therefore its output will remain at value equal to 0. So now the new outputs are 0, 1, and 1. 0, 1 and 1. So this is a third count of your counter. Okay. Now let us see what happens when your previous state is 0, 1, 1 and you apply the clock pulse. So this makes a transition and this I want to show you. Okay. Remaining combinations you can guess. But this I want to specially explain for you. Okay. So your previous states are this Q0 is at logic 1, Q1 is at logic 1 and Q2 is at logic 0. Okay, now let us check the inputs of each and every flip-flop. The input of first flip-flop is permanently tied to logic 1. No question about this. Now output of first flip-flop is given as input to the second flip-flop. So output of first flip-flop is at logic 1 and therefore input of second flip-flop will be at logic 1. Okay. Now what you can see here is both the inputs of AND gate are at logic 1. Okay. So what will be the output of AND gate? Output of AND gate will be 1 into 1 which is equal to 1. So now after all these counts the output of AND gate is becoming 1. Okay, and when it is becoming 1, so this 1 is applied as input to flip-flop number 3. Okay, so now you can see here all the 3 flip-flops they are having logic 1 as input. So all 3 flip-flops will be changing their state when you apply a clock pulse. Okay, so let us see what happens when we apply a clock pulse. So suppose we have applied clock pulse here, then first flip-flop is going to toggle from 1 to 0. Second flip-flop is also going to toggle from 1 to 0. So earlier it was 1, so it will change its state to 0. And third flip-flop input is 1, therefore it is also going to toggle. So it will change its state from 0 to 1. So when your previous state is 0, 1, 1 and you apply a clock pulse, you are getting a new output which is equal to 1, 0, 0. Okay. So in this way, you can proceed to all the counts. It will proceed after 100 to 101. Then it will go to 110. Then it will go to 111. And thereafter, again, it will go to 000. So you can verify this on your own. Okay. So we are not going to spend time in this. Okay. So after this, let us write the truth table of 3-bit synchronous up counter and let us draw timing diagram for this 3-bit synchronous up counter. Okay, so let us do that because these two things are also very important as far as your counter study is concerned. Okay, so I'm going to write the logic diagram. And here I'm going to write the truth table. So truth table will have fields like this: clock, okay, state, and outputs Q2, Q1, and Q0. Because here Q2 is your MSB. Q2 is your MSB. So 0, 1, 2, 3, 4, 5, 6, 7, and again 0. So 0, 1, 2, 3, 4, 5, 6, 7, and again 0. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and again 0, 0, 0. So the same truth table like that of your asynchronous counter. So using this truth table, you must be able to draw a timing diagram. Again, it will be same as that of your asynchronous counter. So you can see output of both are same, but the concept used here or logic used here is different. Okay, so let us draw a timing diagram. One, two, three, 4, 5, 6, and 7 states are there. So this is your clock. After this, you have to draw Q0, then draw Q1, and then draw Q2. Okay, so here again you will see Q0 is changing state at every clock pulse, and that is what you have to show. Earlier it was 0, then it will become 1, again it will become 0, again it will become 1, 0, 1, 0, and then 1. Okay, so this is what is the transition of Q0 is. Now, if you observe Q1, then 2 times it is 0, and then 2 times it is 1, like that. So 2 times it is 0, then 2 times 1, then 2 times 0, and 2 times 1, and again it will go down. Okay. Now, if you see Q2, then it will be 4 times 0, and then 4 times 1, and again it will go down. So here you have to write the data for Q0, Q1, and Q2. So this will be 1, 0, 0, 0, 1, 0, then 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, and last one is 1, 1, 1, and after this 1, 1, 1, again it will be 0, 0, 0. So if you have space, you can draw that 0, 0 waveform also. Okay, you take a screenshot of this for truth table and waveform, and we will move to the next type of counter, that is 3-bit synchronous down counter. Okay, so are you clear about this, how to draw timing diagram from truth table? Write in the chat box. Are you clear? Yes, write in the chat box, and you do it yourself. You practice it yourself in your notebook. It's very simple logic. By observing truth table, you can draw a waveform or a timing diagram. And timing diagrams are very important for sequential circuits. So once you understand how to draw timing diagram, okay. सीचं लेक्चर चालू झालं, but we will stop here. Okay, and tomorrow we will discuss the synchronous down counter, and then we will move to D flip flop. I think we will move to shift register. Yes. Okay, I will end the lecture.